Hello students, welcome to our next module in the Introduction to AI course. In this module, we will continue our discussion on search algorithms, but we'll look at a different type of search algorithms with different criterion for search as well, and these are called local or online search algorithms. This is going to be the lesson structure of this module. We'll start off with local search algorithms. We'll look at a special variant of local search algorithms very widely used, which is called genetic algorithms. Okay. Then we will look at online search algorithms where the states are defined at runtime. As the problem progresses, your algorithm finds out new states. Okay. So with that, let's start with the first lesson, which is local search algorithms. Now, as opposed to the informed and uninformed search algorithms that we looked at in the past couple of modules, where you were trying to go from a start state to an initial state, the problem still remains the same in local search algorithms. You are still trying to go from a start state to a goal state, but the difference is how the search is done. In informed and uninformed, you are doing the search in a systematic manner. So in breadth first, you were expanding the search tree by breadth or level by level. In depth first, you would go down one branch of the search tree all the way to the leaf, and then you would come back up and go down another branch and like that. So basically, the search was very structured. In local search, you make it less structured and kind of depend on stochastic or probabilistic moves. And why do we need these stochastic moves? Because whereas in informed and uninformed search, the path to the goal was important. We had to say which states we were going through. For example, if you remember the path for driving in Romania, going from the initial state Sibiu or Fargas over to Romania, there it mattered which intermediate cities you were going through because that would define your driving route. In contrast, there are many search algorithms or many problems where the path does not matter. It only matters that you reach the goal state. So in those cases, local search algorithms are much more appropriate because they are much faster. So as I say out here, the path to the goal is irrelevant. The goal itself is the solution. As before, the state space is the collection of possible states of the problem. In other words, it's a set of complete configurations. Okay. And the goal is basically to find one state in the state space, in other words, one configuration which satisfies the constraints for the goal. So in such cases, we use local search algorithms, and we need to only keep track of the current state, a single current state, as opposed to, if you remember the variants of A star search algorithm like memory bounded A star, there we needed to backtrack and come back. So we would have to keep a data structure like a queue where we remembered which the past states were. Here you don't need to do that. You just keep track of the current state and you move around. Okay, so how do local search algorithms work? So one of the first things that you require to do in local search algorithms is to understand how good a state is. And to understand how good, the goodness of a state, we associate a value. To calculate this value, we use a function which is called the objective function, or in some algorithms, the fitness function. So basically, this function will take as input the current state and it will return the value of that state. And depending on the value, you can determine whether it's a good state, whether it's not a good state, or in fact, whether it's a goal state, whether you have reached the end goal. Let's delve a bit further to how this works. Let's look at an example. A classical problem that is used in search algorithms is the n queens problem. And here the problem is you have n queens. For example, in the picture, I'm showing 4 queens there, and they're placed on a 4x4 chessboard. Okay. The problem is to find a configuration or a placement of queens on the board so that no pair of queens can attack each other. And as you know, the rules of chess say that a pair of queens can attack if they're on the same row, on the same column, or on the same diagonal. Now on the slide out here, I have shown certain configurations. On the left-hand side, you can see multiple pair of queens can attack each other, same in the middle. And in the rightmost configuration, fewer queens can attack each other. Just these two can still attack each other. So this is still not a solution, but this is still better than where we started from. Okay. Now let us look at an objective function in the context of this n queens problem, but let's do that for an 8x8 board. Okay, so here's an 8 by 8 board and we have 8 queens on it. And the objective function that we define is the number of pairs of queens that can attack each other. So for the configuration that I've shown out here, if you enumerate it and see how many queens are indeed attacking each other, you will see that 17 queens are able to attack each other. So basically, the objective function or fitness function value for this configuration with this placement of queens is 17. So associated with each cell out here, you will see that I have given certain numbers. And these numbers, as I mentioned out here, it is basically the F value that you will get by moving the queen from the same column into that cell. So for example, if I move this queen out here into the cell right below it, then the resulting F value of that configuration would become 12. Okay, likewise, I've shown the values for each of moving the queen from its current location to any place in the same column. And as you can see, 12 is the best value that you are getting out here. So what the local search algorithm should do is it should recommend to move the queen into a cell where the search value, F value, is decreasing the most. So for example, to one of these cells, move, for example, this queen down here or to up here, and that will give the best possible state. And so then from there, we have to continue. And ultimately, the goal is to reach the goal state, basically where no pair of queens can attack each other, basically an F value of 0. If you continue doing that, this is what the solution of the 8 queens problem looks like. So how do we go from this configuration to this goal configuration while using a search algorithm, local search algorithm? So before doing that, let's look at what the objective function or fitness function entails. So if you define a fitness function like this, let's say on a two-dimensional space, then what you end up getting is a landscape, an objective function landscape, which looks something like this. So basically the search space is 2D, which is this plane at the bottom. And then the fitness function basically represents a hill or a mountain or several mountains on them. In other words, what I'm doing is for every point in the search space, this 2D plane at the bottom, I'm calculating the fitness function and plotting that on the upward or the z-axis, let's say out here, and that gives me this landscape. Now my objective is to get to the lowest point in this landscape. My initial state might be anywhere on this landscape. So for example, I start here, or as I show on the picture on the right hand side, I start at this state out here. What my local search algorithm would do is it would tell me to climb down towards another state whose fitness function or objective function value is lower. So if you look at this picture, it would go down the hill. So here I show different initial states. So one is this blue one out here, another is this green. But as you see, for each of them, the path is leading downwards. And my ultimate goal is to reach a point somewhere that is the lowest on this terrain. So in this example, it would be somewhere in this dip. So very close to where each of these 3 algorithms have reached. So how does the search algorithm do that? As I said, from each state, you are just taking a step down. Okay, so basically the first algorithm, which is called hill climbing search, that does exactly that. From the initial state, it takes a state downwards. Now, and it continues doing that. Now, let me mention an important thing, which is till now in the 8 queens example as well, we were saying that the goal state has objective function 0. But remember that came from the fact that we had defined the objective function in such a way that at the goal state, its value would be 0, no 2 queens attacking each other. But in some cases, you might as well define your objective function in some problems in a way that you have to find the maximum value of it. So how would that work with the hill climbing search? It's very easy. From initial state, instead of climbing down, because you're maximizing now, you climb up at each state. Okay, and your objective, ultimately where you reach would be the topmost point in the highest hill that you have there. So that would be a maximization problem for a local search. Okay, so here's the pseudocode for the algorithm for hill climbing search. As the saying goes, hill climbing search in English can be said as it's like climbing Mount Everest in thick fog with amnesia. Thick fog means you cannot see very far, so you can only see locally and determine what the next best step is. Amnesia means you don't remember what you have done in the past, so you just keep track of your current state, and then you go to the next state based on that. You don't remember steps that you have taken or states that you have visited 3 or 4 steps ago. Okay, so this is the pseudocode of the hill climbing algorithm. In this pseudocode, we are solving a maximization problem. So in other words, from each state, we'll climb upwards towards the next state. So the pseudocode looks like this. Like we have done in previous algorithms, we'll take the state representation, we'll convert it into a node structure. Let's call that current. Okay. Then inside the loop, I select from the current state, I generate all the neighboring nodes. I apply the objective function to all of them, and I select the neighbor node which has the highest value for the objective function. Why the highest value? Because now my objective is to climb up. So I want to take the steepest slope upwards. Okay. So then I make sure that the objective function value of the neighboring state is indeed making me go upwards, because I might be already at the highest point in a hill. So all the neighboring points would be lower than me. And so in that case, although I select the highest valued successor of current state, it might actually be lower than the current state. So I have to make sure I am not already at the highest point. So that's what I do in this if statement. I'm checking whether the objective function value of the neighbor, highest valued neighbor, which is given by this uppercase value, that objective function value is indeed higher than my current state. If it is not higher, then I just return current state. I'm the best possible point. And that basically gets out of this loop and also out of this method or function. So that terminates this algorithm. If that is not the case, then I have, or in other words, I have a neighbor state that's better or at a higher point than my current state, then I basically set current to neighbor and I continue. So at the end of this, as you can understand, you will reach the highest point inside your landscape. This is the Python code for doing the same thing. It basically follows the same logic as we saw on the last slide. In order to fill up this algorithm, you still need to do the basic things. That is, you need to define what your state representation looks like. You need to define the implementation or body of the objective function here, which will take the current state, current node, and return numerical value corresponding to however you have defined objective function. And then you have to define this function called move operator, which is basically what we have called successor function. The next state, or basically the return the neighboring state which has the highest value among the neighbors of the current state. So those have to be filled up, but this is the hill climbing search in Python. Okay. Now, hill climbing search is pretty simple, but clearly everything simple comes with its caveats. So let's see what the problem is. So the problem is that, as we saw on the landscape a few slides ago, there might not be one hill, but there might be multiple hills. So I'm showing that on a two-dimensional picture on this slide here. Okay. So if I'm doing a maximization problem, my objective is to reach to this global maximum out here. If I'm using the hill climbing search, then depending on the initial state with the basic hill climbing search algorithm, I might not end up at this top. For example, if I start here and if I'm climbing, I have to climb upwards. So this is the gradient. The arrow shows the gradient going upwards. So in that case, if I use hill climbing, I would end up here. If I were starting somewhere, let's say here, then hill climbing would again end up reaching to this local maximum. On the other hand, if I start somewhere here, I would go up and then I would get stuck at a flat. I don't know, there is no up or down here. So basically it would get stuck here. And then if it keeps moving, sideways moves, if I'm saying that keep moving in the other direction, then it would ultimately fall down here and get worse. Okay. So, and same thing happens here at the shoulder here. Which is sideways move might cause it to fall down here if I'm going on the wrong side. So basically, if I'm unlucky enough, if the initial state is unlucky enough to not start on this hill which has the global maximum, then hill climbing search will not be able to find the solution to the problem. So how do we solve that? So basically, variants of hill climbing search. So before we look at how to solve hill climbing search, let us look at an example of where a local minima has happened. So in this picture, as you can see, I'm saying its objective function value is 1. And if you check, these two queens are able to attack each other. But no matter where you move this queen, you cannot make the h value better than 1, or you cannot get to h equals. So for example, if you move here, these two queens can still attack. So in each of these rows, there's one queen which is attacking. So from here, you cannot get to better than 1. Okay, you can still remain at 1, but not better than 1. In our next lesson, we will continue with that discussion and look at variants of the hill climbing search algorithms to see how to rectify this local minima problem or local maximum problem and make sure that the algorithm ends up at the best point, maxima or minima.